So before we do the rest of the notes, we need to do net ionic equations. And net ionic equations are for things that are in solution. Remember when we were doing double replacement reactions or even single replacement, we had to say if things were aqueous or not, okay? So the way that we're going to do this is you're going to start with the balanced molecular formula, just like what we've been doing. And then the next step is anything that is aqueous, we are going to break apart, because in actuality it's not together in a solution, it's actually breaking apart and swimming around as different ions. So we look at this one and we know that sodium chloride is aqueous because it tells us, but we also know that because it is a group 1 metal. So we're going to say that we have 2 sodium ions and they are aqueous. This is on the second page of the handout, and then we're going to do some that are not already done for us. Then we have 2 chlorine, also aqueous, plus we have a lead, which is aqueous, because remember when it's aqueous they're not together in actuality. Okay, and then on the other side of the equation we break apart what's aqueous, but if it's a solid we leave it together because it's a precipitant, it's fallen out of the solution. So we have 2 sodium on that side, and then we have 2 nitrates, and then I ran out of room, and we have the lead 2 chloride. So to get our net ionic, we're going to look at what appears the same on both sides. And when I say the same, I mean exactly the same. They're both aqueous on both sides, or they're both something else on both sides. So what things in this equation appears the same on both sides? Huh? The sodium, so we're going to mark out sodium and say we're not going to include that. What else? The lead is not the same on both sides. It's aqueous on one side and it's bound up in a solid on the other side. So it's not the same on both sides. The nitrates. So we're going to throw out the nitrates. Okay? And everything else is different. The chlorine is different. It's aqueous on one side and bound up in a compound on the other side. So our final net ionic equation is we write what's left, what we didn't mark out. So we would say 2 chlorine, which is aqueous, plus a lead, which is aqueous, and that forms lead 2 chloride. So when we do this, that's an S, sorry. When we do this reaction, and the only thing that's actually reacting is the chlorine and the lead, and they're making the lead 2 chloride. The sodium and the nitrates are spectator ions, okay? And spectator ions do not participate in the reaction. They exactly what you do as you're a spectator at a sport. You're just watching what's going on. You're not participating, okay? So that's what a spectator ion is. And so this is where we got to know our solubility rules. It's going to come into play. In this packet, I've given you a copy so you don't have to go find them. Also on the first page, you got to know your strong acids and strong bases, because strong acids completely dissociate and break apart. Weak acids do not. Okay? Any questions on that? I'm going to do some more examples, but any questions on what I did and why I did it? Okay. Let's do another one. So in the next page is example 1. We'll do that. Before I delete this, everybody have it? Okay. So we're going to start out with iron 3 nitrate. So how do I write iron 3 nitrate? Okay. Nitrates are always soluble, so we're going to write AQ behind it. And we have potassium hydroxide. Group 1 metal, potassium, always aqueous, always soluble, so it'll be aqueous. And then double replacement, so we're going to do inside, outside. So my thing is going crazy. So what's it going to make? It's going to make iron 3 hydroxide, so FeOH3. What does it say? What do our solubility rules say about hydroxides? There, it's on the next page. Hydroxides, insoluble unless they're with those things. Well, so this makes this a solid because it's not one of the exceptions. And then we're going to make potassium nitrate. And there we have group 1 and nitrates, which are always soluble. So we're going to write AQ. So now on the next step, we're going to break everything apart that's aqueous. So we're going to say Fe 3 plus aqueous plus 3 nitrates aqueous. Oh, we need a balance. Sorry, my bad. There we go. We're going to do the same thing on the product side. A solid, do we break apart a solid? No, we leave that all together. And then we have 3 potassium plus 3 nitrates. So what appears the same on both sides? The what? I heard someone say nitrates. And the potassium. So we're going to take those out. So that means our final net ionic equation is going to be Fe 3 plus 3 OH minus. That's very messy. Sorry, that's an OH minus. And it's going to make FeOH3. So that's what's actually happening in that reaction. Okay? So as you're doing this, some of you will need to do the middle step because it'll help you. But some of you will be able to recognize right away that whatever was my solid, I got to do the 2 things that make it up. Okay? If it's making liquid water, we have to include that as well because liquid water, it does not break apart in solution. Okay? The only thing you're going to break apart are your aqueous things. If it makes a gas, we don't break up a gas. We only break up the aqueous. Okay? Any questions so far, or does it seem pretty straightforward and easy? Yes? You can only cancel them out if they appear the same on both sides. So like sodium, or in this case potassium, was aqueous on both sides. Okay? So that's why I was able to cancel it out because it didn't change. It started out aqueous, it ended aqueous. So that's why I was able to cancel out. The reason it's the same on both sides is because we balanced it first. You should never have potassium in a solid compound. Huh? We will not be breaking up water, we would form water. Yes?
Why do we keep the iron oxide together but not the...
Because if we look at our solubility rules on iron oxide, it's insoluble, so it forms a solid. So it actually reacted and formed something. So basically, if I mix together a solution of iron, 3 nitrate, and sodium, or not sodium, potassium hydroxide, they would be 2 clear liquids. And when I would mix them together, I would probably get, I think it's yellow. I think I get a yellow solid out of that. So this is what actually is happening. I would still, in the liquid part that held the solid, would still have potassium and nitrate dissolved in water, and some water. These are all, when we say aqueous, remember, we're assuming they're dissolved in water. Okay? But if it forms a precipitant, or in the case of the solubility rules, we say insoluble, then that's actually what's forming. Okay? So I want to do a single replacement one to show you, and I want to do an acid-base one too. Okay? Which are not exactly some of these ones, but I'm going to make them up. Okay? So everybody have that? So if you want to cross out like your example 2, and I'm going to do a different one because I think it'll help you. So let's do, name an acid you want me to do? Sulfuric? Okay. Give me a strong hydroxide. Group 1 hydroxide. Pick one. Lithium hydroxide. Okay. So that's an acid and a base. So remember, they make an ionic salt and water. And it makes liquid water. So we're going to have lithium sulfate, oops, which lithium is a group 1, so it stays aqueous, and then we form water. So let's go balance. I need 2 here. And now how much, what do I need in front of water? Someone say 2. Thank you. Okay, so now it's balanced. So let's break apart what's aqueous. So we're going to have 2 hydrogens plus a sulfate plus 2 lithiums plus 2 hydroxides. And when we break apart on the other side, we have 2 lithiums plus a sulfate plus H2O, 2 H2O liquid. Crossing out what appears the same on both sides. So what appears the same on both sides? Lithium. Go by lithium. Water is not the same on both sides. Sulfate. I heard someone say sulfate. So that my net ionic becomes 2 hydrogen plus 2 hydroxides, both aqueous, and they form 2 H2O liquid. Yes.
Can you reduce that?
Hold on, he's asking a question. What?
So we just ignore like the rule that like makes up hydrogen H.
I can't hear you. Can you speak up?
We ignore, so for this we ignore like the rules that make like hydrogen H2 and like chlorine H2 or what's the other?
No, if they're aqueous, are you talking about the Brinkelhoffs?
Yeah.
Only if you're forming one, but you have to know, because there's no Brinkelhoffs here at all, because everything's in a compound. Okay. Yes, you actually could reduce that if you wanted to. Now up here we couldn't, because then it wouldn't bounce it. But if you wrote down H plus OH yields H2O, that is the correct net ionic, because you could, in that case, reduce it. Yes.
Do we have to write the plus and minus on the charges?
Oh, absolutely. There. Forgot it. Yeah, you always have to include the charges in your net ionics. Okay? So that was an acid base. Let me show you. I don't think any single replacements show up on your worksheet, but I want to show you just in case. So let's do another example. So let's see. Let's use lithium again, because we know lithium is going to replace everything, right? So lithium is going to be a solid, and we're going to add it to, let's add it to calcium sulfide. Okay? Actually, let's not add it to, let's do it to calcium sulfate. No, because no, I need to do something that's aqueous. Calcium chloride.
Are we crossing out example 3?
Yeah. Well, I just changed colors. Calcium chloride would be aqueous. So in a single replacement reaction, we want to know, will lithium replace calcium? And what do you remember about lithium?
Oh, we can replace it.
Top dog, it replaces everything. Yes.
Why is lithium a solid if it's a component?
Right. It's by itself, it's a solid. Yeah. It's not in a compound.
Do CAS.
Huh?
Why don't we do CAS?
I believe calcium sulfide is insoluble.
No, it's soluble.
Sulfide? Oh,
Group 1, group 2 metals and ammonium.
I couldn't remember that one. Yeah, because I don't deal with the sulfides. But we could have done calcium sulfide then. Yeah. I was thinking it was insoluble. Because the sulfides I have to go check, because we don't deal with sulfides that much. So I didn't want to accidentally do one that was. Okay. So lithium will replace calcium, so that means we get lithium chloride. Right? No, we don't. Sorry. Lithium chloride, which is aqueous, plus calcium solid. So I need to balance. I'm going to put a 2 here and a 2 here. I'm balanced. So now let's break apart anything that's aqueous. So I have to have 2 lithium solid plus a calcium 2 plus 2 chlorine minus aqueous. And then over here I would have 2 lithium plus 2 chlorine minus. Both of those are aqueous. And then plus calcium solid. So what appears the same on both sides? I'll give you a hint. It's only one thing that appears the same on both sides. Yes?
Not lithium,
How
not
come
lithium.
one's calcium
Gas.
aqueous and one's a solid?
CO.
Because in a single replacement, when it kicks calcium out, calcium is a solid by itself.
But when it's together with chloride, then it's.
Yeah, because now it's an ion. But whenever lithium kicks, remember when we kick something out and it's just the element by itself, then you have to go what its standard state is, and the standard state of calcium is solid. And what did we say was the same on both sides? The chlorine. So we're going to mark out chlorine. So that means my overall net ionic would be 2 lithium plus a Ca2 plus, which is aqueous, yields 2 lithium aqueous plus a Ca. So that would be my net ionic. When we get to redox reactions later in the year, you'll find that this is actually a redox reaction here. You'll find that in addition to your elements being balanced, so does your charge has to be balanced. And if you look at this, both sides have a 2 plus charge because your charges have to be balanced as well. But that's when we get to redox, which are my favorite ones to balance. I love them. Okay? All right.